Welcome to Schovia, where we make AI concepts feel like everyday ideas. In the next few minutes, you'll understand what loss actually is without equations. We are going to do three things. We'll visualize the loss as the physical gap between the guess and the truth. We'll walk through the error landscape, which is the exact map your model uses to get smarter. We'll show why accuracy cannot teach a model at all. And by the end, when you see a training plot that says loss is going down, you'll know exactly what's happening. When you first create an AI model, whether it's a simple regression or a massive neural network, it starts as a blank slate. It hasn't learned anything yet. Its weights are random. If you're wondering what a model and its weights mean, please check out our video on what is an AI model. Coming back to our model, when our model is not trained yet, if you show it a picture of a cat, it might guess toaster. Or if you ask it to predict the price of a house, it might guess -$5 or something like that. So, how does it get from there to a chat GPT or a self driving car? It needs something to calculate how far off the market is so that it can adjust its course. That something is the loss function. Let's use an example to go over this. Imagine playing the hot and cold game. You're blindfolded and you're trying to find a hidden object. If I just tell you, no, you haven't found it yet, a simple yes or no, right? You're never going to find it. You don't know which way to move. But if I tell you, you are 10 meters away, now 8 meters, now 5 meters, or now 15 meters, which is colder, suddenly you can navigate. A loss function provides that distance, gives you numbers that tell you how wrong your prediction is. In simple terms, a loss function is a math formula that measures the distance between what the model predicted and what the actual value is. A low loss means the model is doing great. High loss means the model is failing. The goal of machine learning is simple: minimize the loss and make that number zero if possible. If we plot the loss values of all possible weight values, let's say there are two weights and we plot this in 3 dimensions, it might look something like this. This is called the loss landscape. The altitude represents the loss. The peaks are where the model is not good. The bottom of the valley is where the model is smart. The model starts here at the top, blindfolded, and it wants to get to the bottom. This is where the loss function powers the learning. Because the loss function is a smooth mathematical curve, we can calculate the slope of the ground right under our feet. The loss function tells the model if you change your internal weights this much to the right, your error will go down. Without a loss function, the landscape would be flat. The model wouldn't know which way is down. But with it, the model can slide down the mountain step by step until it reaches the bottom. This process is called gradient descent. Note that different problems require a different kind of loss function. If you're predicting numbers like house prices, we usually use mean squared error. It takes the error, which is the distance between what you predicted and what the actual value is, and then it squares it. Why square it? Well, square it because that would punish the big mistakes heavily. Being off by 10 is way worse than being off by 1. And squaring it forces the model to fix the big outliers first. But if you're predicting categories like a cat or a dog, then distance doesn't make sense, right? You can't say that your prediction is 5 meters away from a cat or something like that. Here we use log loss or cross entropy. This measures confidence. If the image is a cat and the model predicts 90% chance it's a cat, the loss is tiny. But if the model predicts 99% chance it's a dog, then the loss explodes. So it screams at the model for being confident incorrectly. Here is a question you might have. Why do we train our model on a loss? Why don't we train it on something like accuracy? Well, it turns out accuracy is not that useful for training because accuracy is a step function. If a model predicts 0.49 probability for spam incorrectly, right, instead of classifying it as not spam, and then let's say the model improves slightly and it predicts that something is spam by 0.499, right? It's still wrong, but then it has made an improvement from what it predicted previously. However, in both cases, the accuracy didn't change. The model tried to learn and it did learn in the right direction, but the accuracy metric gave it zero feedback. It stayed flat. On the other hand, a loss function is smooth. Moving from 0.49 to 0.4999 lowers the loss, even if it doesn't flip the result yet. It gives the model constant granular feedback that, hey, you are getting warmer. Loss is for the machine to learn. Metrics like accuracy are for humans to judge. So, next time you see a model training and the loss curve is going down, imagine that hiker sliding down the mountain. The math is guiding it from random guessing to intelligence. But knowing how the model learns is only half the battle. You also need to know what happens when it memorizes the training data too well and it fails in the real world. That is called overfitting, and you can check out what that means in the video right here. Thank you for joining us on Schovia Labs. Hit that subscribe button for more eye opening insights, and as always, stay curious.